Metallurgy is a domain of materials science and engineering that studies the physical and chemical behavior of metallic elements, their intermetallic compounds, and their mixtures, which are called alloys. Metallurgy is also the technology of metals, the way in which science is applied to the production of metals, and the engineering of metal components for use in products for consumers and manufacturers. The production of metals involves the processing of ores to extract the metal they contain, and the mixture of metals, sometimes with other elements, to produce alloys. Metallurgy is distinguished from the craft of metalworking. Metallurgy is subdivided into ferrous metallurgy and non-ferrous metallurgy or colored metallurgy. Ferrous metallurgy involves processes and alloys based on iron, while non-ferrous metallurgy involves processes and alloys based on other metals. The production of ferrous metals accounts for 95% of world metal production. Etymology and pronunciation: the word was originally an alchemist's term for the extraction of metals from minerals, the ending -gy signifying a process, especially manufacturing. It was discussed in this sense in the 1797 Encyclopaedia Britannica. In the late 19th century it was extended to the more general scientific study of metals, alloys, and related processes. The roots of metallurgy derive from ancient Greek, I1/4 I micron II plus or minus I cubed IY, metallurga cubed S, worker in metal, from I1/4 II plus or minus I 1/2, ma copyright Hallen, metal plus A1/4 II cubed II 1/2, a copyright RGON, work. In English, the pronunciation is the more common one in the UK and Commonwealth. The pronunciation is the more common one in the USA, and is the first listed variant in various American dictionaries. History: the earliest recorded metal employed by humans appears to be gold, which can be found free or native. Small amounts of natural gold have been found in Spanish caves used during the late Paleolithic period, c. 40,000 BC. Silver, copper, tin and meteoric iron can also be found native, allowing a limited amount of metal working in early cultures. Egyptian weapons made from meteoric iron in about 3000 BC were highly prized as daggers from heaven. Certain metals can be recovered from their ores by simply heating the rocks in a fire, notably tin, lead and copper, a process known as smelting. The first evidence of this extractive metallurgy dates from the 5th and 6th millennium of BC and was found in the archaeological sites of Modank, Yamovac and Pliknik, all three in Serbia. To date, the earliest evidence of copper smelting is found at the Belivode site, including a copper axe from 5500 BC belonging to the Vino culture. Other signs of early metals are found from the 3rd millennium of BC in places like Palmyra, Los Millers, and Stonehenge. However, as often happens with the study of prehistoric times, the ultimate beginnings cannot be clearly defined and new discoveries are both continuous and ongoing. These first metals were single ones or as found. About 3500 BC, it was discovered that by combining copper and tin, a superior metal could be made, an alloy called bronze, representing a major technological shift which began the Bronze Age. The extraction of iron from its ore into a workable metal is much more difficult than for copper or tin. The process appears to have been invented by the Hittites in about 1200 BC, beginning the Iron Age. The secret of extracting and working iron was a key factor in the success of the Philistines. Historical developments in ferrous metallurgy can be found in a wide variety of past cultures and civilizations. This includes the ancient and medieval kingdoms and empires of the Middle East and Near East, ancient Iran, ancient Egypt, ancient Nubia, and Anatolia, ancient Nok, Carthage, the Greeks and Romans of ancient Europe, ancient and medieval China, ancient and medieval India, ancient and medieval Japan, amongst others. Many applications, practices, and devices associated or involved in metallurgy were established in ancient China, such as the innovation of the blast furnace, cast iron, hydraulic-powered trip hammers, and double-acting piston bellows. A 16th-century book by Georg Agricola called De Re Metallica describes the highly developed and complex processes of mining metal ores, metal extraction and metallurgy of the time. Agricola has been described as the father of metallurgy. Extraction. Extractive metallurgy is the practice of removing valuable metals from an ore and refining the extracted raw metals into a purer form. In order to convert a metal oxide or sulfide to a purer metal, the ore must be reduced physically, chemically, or electrolytically. Extractive metallurgists are interested in three primary streams: feed, concentrate, and tailings. After mining, large pieces of the ore feed are broken through crushing and or grinding in order to obtain particles small enough where each particle is either mostly valuable or mostly waste. Concentrating the particles of value in a form supporting separation enables the desired metal to be removed from waste products. Mining may not be necessary if the ore body and physical environment are conducive to leaching. Leaching dissolves minerals in an ore body and results in an enriched solution. The solution is collected and processed to extract valuable metals. Ore bodies often contain more than one valuable metal. Tailings of a previous process may be used as a feed in another process to extract a secondary product from the original ore. Additionally, a concentrate may contain more than one valuable metal. That concentrate would then be processed to separate the valuable metals into individual constituents. Alloys. Common engineering metals include aluminium, chromium, copper, iron, magnesium, nickel, titanium and zinc. These are most often used as alloys. Much effort has been placed on understanding the iron-carbon alloy system, which includes steels and cast irons. Plain carbon steels are used in low-cost, high-strength applications where weight and corrosion are not a problem. Cast irons, including ductile iron, are also part of the iron-carbon system. Stainless steel or galvanized steel are used where resistance to corrosion is important. Aluminium alloys and magnesium alloys are used for applications where strength and lightness are required. Copper-nickel alloys are used in highly corrosive environments and for non-magnetic applications. Nickel-based superalloys like Inconel are used in high-temperature applications such as turbochargers, pressure vessel, and heat exchangers. For extremely high temperatures, single-crystal alloys are used to minimize creep. Production. In production engineering, metallurgy is concerned with the production of metallic components for use in consumer or engineering products. This involves the production of alloys, the shaping, the heat treatment and the surface treatment of the product. The task of the metallurgist is to achieve balance between material properties such as cost, weight, strength, toughness, hardness, corrosion, fatigue resistance, and performance and temperature extremes. To achieve this goal, the operating environment must be carefully considered. In a saltwater environment, ferrous metals and some aluminium alloys corrode quickly. Metals exposed to cold or cryogenic conditions may endure a ductile to brittle transition and lose their toughness, becoming more brittle and prone to cracking. Metals under continual cyclic loading can suffer from metal fatigue. Metals under constant stress at elevated temperatures can creep. Metalworking processes. Metals are shaped by processes such as casting. A molten metal is poured into a shaped mold. Forging. A red-hot billet is hammered into shape. Flow forming. Rolling. A billet is passed through successively narrower rollers to create a sheet. Laser cladding. A metallic powder is blown through a movable laser beam. The resulting melted metal reach a substrate to form a melt pool. By moving the laser head, it is possible to stack the tracks and build up a 3D piece. Extrusion. A hot and malleable metal is forced under pressure through a die, which shapes it before it cools. Sintering. A powdered metal is heated in a non-oxidizing environment after being compressed into a die. Metalworking, machining. Lathes, milling machines, and drills cut the cold metal to shape. Fabrication. Sheets of metal are cut with guillotines or gas cutters and bent and welded into structural shape. Cold working processes, where the product unregistered trademark S shape is altered by rolling, fabrication or other processes while the product is cold, can increase the strength of the product by a process called work hardening. Work hardening creates microscopic defects in the metal, which resist further changes of shape. Various forms of casting exist in industry and academia. These include sand casting, investment casting, die casting and continuous casting. Heat treatment. Metals can be heat treated to alter the properties of strength, ductility, toughness, hardness or resistance to corrosion. Common heat treatment processes include annealing, precipitation strengthening, quenching, and tempering. The annealing process softens the metal by heating it and then allowing it to cool very slowly, which gets rid of stresses in the metal and makes the grain structure large and soft-edged so that when the metal is hit or stressed it dents or perhaps bends, rather than breaking. It is also easier to sand, grind, or cut annealed metal. Quenching is the process of cooling a high-carbon steel very quickly after you have heated it, thus freezing the steel's molecules in the very hard martensite form, which makes the metal harder. There is a balance between hardness and toughness in any steel, where the harder it is, the less tough or impact-resistant it is, and the more impact-resistant it is, the less hard it is. Tempering relieves stresses in the metal that were caused by the hardening process. Tempering makes the metal less hard while making it better able to sustain impacts without breaking. Often, mechanical and thermal treatments are combined in what is known as thermomechanical treatments for better properties and more efficient processing of materials. These processes are common to high-alloy special steels, superalloys and titanium alloys. Plating. Electroplating is a common surface treatment technique. It involves bonding a thin layer of another metal such as gold, silver, chromium or zinc to the surface of the product. It is used to reduce corrosion as well as to improve the product's aesthetic appearance. Thermal spraying. Thermal spraying techniques are another popular finishing option, and often have better high-temperature properties than electroplated coatings. Microstructure. Metallurgists study the microscopic and macroscopic properties using metallography, a technique invented by Henry Clifton Sorby. In metallography, an alloy of interest is ground flat and polished to a mirror finish. The sample can then be etched to reveal the microstructure and macrostructure of the metal. The sample is then examined in an optical or electron microscope, and the image contrast provides details on the composition, mechanical properties, and processing history. Crystallography, often using diffraction of X-rays or electrons, is another valuable tool available to the modern metallurgist. Crystallography allows identification of unknown materials and reveals the crystal structure of the sample. Quantitative crystallography can be used to calculate the amount of phases present as well as the degree of strain to which a sample has been subjected. See also, archaeometallurgy, CALFAD, carbonyl metallurgy, cupellation, experimental archaeometallurgy, Georg Agricola, gold beating, gold phosphine complex, metallurgical failure analysis, mineral industry, pyrometallurgy. References. External links, media related to metallurgy at Wikimedia Commons, learning materials related to topic, metallurgical engineering at Wikiversity, metallurgy for the non-metallurgist.